Okay, this is 2009 question 9. I'm hoping to keep this quite short because it's just repetition of what we've already come across really in previous questions. Okay, so explain activation energy. Alright, so the amount of energy required for an effective collision to take place, and an effective collision then a collision where a product is actually formed, where two reactants collide off each other and a new product is formed. Okay, make sure that you see all parts of this question. So this part of the question doesn't even have maybe a letter or number associated with it, but it has 6 parts going. Okay, so make sure you include it as part of part A. Okay, so describe how the time for the reaction between the solutions of HCl and sodium disulfate was obtained. Okay, so add your two reactants together, so add your hydrochloric acid and sodium disulfate together, start your stopwatch. Okay, observe the reaction until you can't see the X anymore, the print becomes invisible, or you can't see the black ink or the black X that's underneath the conical flask anymore, and you stop your stopwatch. Okay, and you just record your time. Okay, so hopefully a pretty simple 6 marks there. In a reaction mixture, what effect, if any, does an increase in temperature of 10 Kelvin have on each of the following? So the number of collisions would increase, as if you increase temperature, that means that the increase in temperature is resulting in an increase in energy, okay, an increase in heat energy. So that means your number of particles have greater energy, so they're going to be moving around more, so there's going to be more collisions. The effectiveness of the collisions will increase. Okay, that will actually increase more maybe than the number of collisions. Okay, so there'd be a greater increase. So there'd be a slight increase in the number of collisions. There'd be quite a large increase in the effectiveness of the collisions, for the same reasons really, that the particles have more energy. So when they collide, they're colliding with more energy, and it's more likely that an effective collision will actually take place and a product will be formed. And then part 3, the activation energy, there'll be no effect on the activation energy. The activation energy is not temperature dependent. Okay, so part B then, the catalytic oxidation of methanol using platinum wire is illustrated in the diagram. State 1 observation made during the experiment. Okay, so this is a demonstration that is actually in your textbook if you go to the relevant section. Okay, so in this there are a couple of observations that can be made. The wire could glow. There could be a flame, small flame. There could be a popping sound. Or there could also be an odor, and that odor is of methanol. Okay, so odor of methanol. Okay, so that they are some of the observations that might be made. The wire glowing is the most obvious one. Okay, the glowing wire. Name any 2 products of the oxidation reaction. Okay, so 2 products then. We mentioned one there. Methanol is one. So methanol, as I say, is one product. Another product is hydrogen. Okay, and the last one is water. Okay, so there are 3 products. Unfortunately, they just have to be learned off. Okay, and some of the observations might give a kind of clue as to what products are formed. I suppose that you have the odor of methanol, you have a popping noise as well. Okay, they can give clues as to what's going on. Okay, but they really just have to be learned off, unfortunately. Okay, what type of catalysis is involved in this reaction? Okay, so we have our reactant, I suppose, our methanol. Okay, and we have our catalyst. So sorry, our methanol is liquid. Okay, our catalyst is our platinum wire, and that's solid. Okay, so that means one is in liquid state, the other one is in solid state. So they're in two different states. Okay, or they're in two different phases. So they're heterogeneous. Okay, they're heterogeneous. It's a heterogeneous catalysis. It could also be regarded as surface adsorption. Okay, so if you look at your surface adsorption theory, then that's what happens. Okay, the reaction happens on the surface of the catalyst. So the particles are brought closer together on the surface of the catalyst, and that is why the reaction happens a little bit faster. And of course, it lowers the activation energy. Okay, as well, for the same reason. Okay, for the reason of that surface absorption, and the activation energy is reduced. Okay, then explain how a catalyst poison interferes with this type of catalysis. So the catalyst poison is preferentially adsorbed, so it'll adsorb onto the surface of the catalyst before your reactants are. Okay, or it'll block the active sites, so it'll block the sites where the reactions can take place. So if you think of that, you have your particles, you have your surface area. So what you're essentially doing is you're reducing the amount of surface area where reactions can take place because they're being blocked by this catalyst poison. So the catalyst poison adsorbs onto the surface of your catalyst and blocks the sites where the reaction can take place. The last part of the question then, give another example of a reaction which involves the same type of catalysis, indicating clearly the reactants and the catalyst. Okay, there are so many of these on your course. Okay, the first one that pops to mind would be the decomposition of hydrogen peroxide, so H2O2, and using manganese dioxide in that as a catalyst. Okay, so here's a list okay, of them that are all on these are, for the most part anyway, are on your Leaving Cert course. Okay, so some of them should be familiar to you, so definitely have one or two of them. Okay, and those of you especially that I suppose like the organic chemistry section and that sort of thing, I would recognize some of these. Okay, yeah, okay, so make sure you know one or two examples of those as well. Okay, and that is, remind myself of the year again, 2009, question 9. Okay, I have question 7, it's question 9, 2009, question 9.